Welcome back, everyone, after the break. And we are very happy to have the first lecture of our second series of lectures and have Nabil Iqbal give us an introduction to generalized global symmetries. And again, if you have any questions during the lecture, just raise your hand, and we will have our question session as well in the break and after the lecture, if it's not as urgent. Good, then. Thank you very much. The stage is yours.
Okay, thank you. Is the microphone working correctly? Seems like it. Okay, hello everyone. I want to begin by thanking the organizers for inviting me to be here and for putting together what seems like a wonderful school. So for those of you who haven't met yet, my name is Nabil Iqbal. I'm a professor at Durham University in the UK. I work on random things, but like applications of quantum field theory, holographic duality, things like that mostly. Okay, so these lectures are going to be about generalized global symmetries. And this is a somewhat new idea in quantum field theory. It started maybe 10 years ago, I'd say. It really started to enter the mainstream. And there are some aspects of this field that I kind of feel that everyone who is a physicist should know something about. They're sort of very basic ideas that could honestly be taught at the textbook level without too much difficulty. And I kind of feel like even if you don't work in this area specifically, if you think about quantum field theory or you think about gauge theory, the ideas can be useful. So I'm going to try to convey to you some of that, all right? So there are lecture notes here. I think you've received the link already. They'll be updated as we go. They're not completely finished yet, even for the lectures that I'll be giving here. So refer back to that frequently. Okay. So let's get started. I want to start in a sort of very vague and fluffy way, okay? So I want to ask you, what are the phases of matter in the universe, okay? Maybe another way to phrase that question is, instead of what are the phases of matter, really I'm asking, what can exist, okay? What can we have? How can matter arrange itself, okay? And here I've put some phases of matter on the board, okay? Now, you can sort of see maybe that I've kind of arranged these in order. There's a sort of ordering here, which basically means that I would say I have put the easy phases of matter on this side and the harder ones on this side, okay? This is how I've sort of arranged these here. So on this side, for example, we have the baby ones that we all know about, right? The matter comes in solid, liquid, and gas. Gas is the easiest, okay? And we have solids and liquids. And then as you begin to learn more things about physics, you realize there are other phases of matter, right? There are magnets. Magnets can be either ferromagnetic or paramagnetic. Those are two different phases. I've not written them here. And then more things start to happen, right? If you have a liquid, and you cool it down enough, sometimes it becomes what's called a superfluid. You get a Bose-Einstein condensate, which is a different phase of matter from the liquid, all right? And then again, more things can happen. We have metals, right? I mean, metals, something is going on with metals. You apply a current, you apply a voltage, a current flows. There's clearly something different happening there. And then again, just to list the things that I've put here, light, the vacuum supports electromagnetic excitations. That's a thing that I'm listing here. We have QCD, which is the phase of matter describing the hadrons and baryons. As we keep going, we get into more and more sort of exotic things. So superconductors exist. There's something called the fractional quantum Hall effect, which you might have heard of. I'll talk more about it in a little bit. And we continue to get harder, right? There's the quark-gluon plasma, which is what you get if you heat up QCD enough. The quarks and gluons come loose and you get something. And there's also ordinary plasma. In fact, if you Google phases of matter, Google says there are 4 phases of matter: solid, liquid, gas, and plasma, which is also what I learned in school a long time ago. Did people learn that in school, that there are 4 phases? Did you wonder what's up with plasma? Why is that a different phase from, I don't know, liquid, for example? We'll discuss that actually towards the end of this lecture series. There's really a difference. It is different, and for a reason I've put it far to the right of liquids, okay? Okay, so this is this easy hard spectrum, and way, way, way over here, we have gravity, okay? Okay, it's really far that way. Okay, so these are some things. Does anyone have any other phases they want me to add to this? We can put it here. Anyone? No? Okay, I've included everyone's favorite phase of matter. Okay, that's great. Now, if you look at this, you might sort of think there's a sort of natural dividing line here between the easy ones and the hard ones. And the truth is, I would put that line somewhere over here, okay? In that these ones you typically learn about in a normal undergraduate physics curriculum, right? And then these ones you don't, okay? These somehow seem harder, okay? And if you think about what is it that makes these harder, the thing that sort of all of these guys on this side have in common is that they sort of all involve, in some form or another, some sort of gauge theory, right? In fact, so does light, but we just learned about that early enough that we're not stressed out about the gauge theory aspect of it, but you could have put this line maybe like this if you really care about where to put light. So there's a sense in which the things that involve gauge theory seem harder and more complicated. And these lectures are really going to be about ways to understand gauge theory in a sort of somewhat new and I think productive way. And so now let me ask you, again, just to motivate, I want to ask you all another question. And this question is what is gauge theory? Okay. Okay. So this is a sort of oh, sorry. This one. Yes. Okay. So let me ask another question, which is what is gauge theory? Okay. So this is again a question that sounds really easy, right? So for example, here. This is a gauge theory, right? Okay, gauge theory, good. Okay, everyone agrees this is a gauge theory, right? Okay. Now how about this? So this A was a one-form field. Here, this theta is or just a normal gauge field. This theta here is a scalar, okay? I'm asking you, the integral of d3x, a massless scalar in 3 dimensions. Is this a gauge theory? Would anyone say this is a gauge theory? I'm seeing no one to stand up for the gauge theoriness of this. But something sleazy happening here, because the truth is, these two theories are the same, right? There's a sort of nonlinear change of variables you can do, or sorry, linear change of variables you can do. This is called particle-vortex duality. It's a simple thing. We're going to do this in the exercises. And therefore, these two theories are actually the same theory, okay? So if this is a gauge theory, then this one is also a gauge theory, whether you like it or not, right? But that should leave you feeling uncomfortable. What do you mean this is a gauge theory? There is no gauge symmetry in this description, even though there is one in there, right? So this sort of example might lead you to think that there's something that you're maybe not quite understanding about what does it really mean to be a gauge theory. And the truth is there are many examples like this, okay? So here I'm just going to give you 2 more of my favorites, and then I promise I'll stop giving examples. Another example that I like is if you take, for example, quantum gravity. It looks different than the previous example. But take quantum gravity. Is quantum gravity a gauge theory? That's a little bit confusing, but if you ask about quantum gravity on ADS5 cross S5, okay, in other words, a chunk of ADS space with an extra 5 sphere, then it's definitely true that this is a gauge theory, because this is definitely equivalent to n equals 4 super Yang-Mills SUN gauge theory, okay? These are the same thing, and so then therefore this is also a gauge theory in one fewer dimension, but it's also a gauge theory, all right? And similarly, one more example that I'm going to give is if you take a bunch of electrons and you sort of confine them to a plane, okay, and then you apply a very strong magnetic field to this system, then something very remarkable happens, which is that you enter a new phase of matter where, sort of philosophically speaking, the electron splits into 3 different pieces, okay? Or not necessarily 3, the simplest state is when it splits into 3, but it splits into n different pieces, okay? That's what's called the fractional quantum Hall effect, all right? And it is described at long distances by a Lagrangian which looks like this, okay? This A is not the photon. It's an extra emergent gauge field that describes the long-distance dynamics of the electrons in a magnetic field. This one actually exists in real life, okay? It was discovered experimentally first, and then the theory was developed. So what that means is a bunch of electrons in a magnetic field can sometimes be described by a gauge theory, okay? So what I'm trying to get at with this is that the question, what is gauge theory, is a confusing one. And it would really be nice if we had a way to describe it that was sort of description independent, that really captured the essence of what it means to be a gauge theory in a way that doesn't care about, dualities or things like that. You can ask, what is the point of a gauge theory? And that is basically what I'm going to try to tell you about. I'm going to explain it as a new way to think about global symmetries that lets you capture the essence of what it means to be a gauge theory. And that's what we're going to discuss. Okay. So this is all basically motivation. Are there any questions before we keep going? No. Any questions? I should say you should please interrupt at any time with questions. I think that makes the whole thing much more fun. And yes, question.
So what's this object, dA?
dA?
Yeah.
Oh, very good. Sorry, some notational stuff. I'm going to be using differential forms notations a lot. Are people happy with the differential forms notation? No, most people are? Okay. So dA is just a 2 form, which means that it's an antisymmetric 2 form like this. And I just mean that A is a vector field, and the components of the 2 form dA are just this. Okay? That's what is that answering your question? Or
Yeah, so
yeah.
this is a 2 form, and then you have D3x is a 3 form, so you do it.
Oh yeah, sorry, I'm terribly mixing notation here. The right way to write this in form notation, the way to write this should be over some 3-manifold dA wedge star dA is the correct way to write this in form notation. I'm going to do this anyway. I apologize in advance. But if there's ever any question, it should work out. But if there's any question, just ask me. Yeah. Excellent. Yeah. Yeah. Okay. Good. Other questions? Yeah. Okay. Right. Okay. So and also I know that there's a reasonable mix of audiences here. So if I use a concept that you're not familiar with, please raise your hand and ask me. Or you can, of course, just ask me afterwards, and I'll give references to everything. Okay? Okay. So now let's get started with the actual content of this. So what I'm going to do now is talk about, for a while, about ordinary global symmetries before getting into generalized global symmetries. Okay? And this is just to remind everyone what we're up to and to make sure everyone's on the same page. And then after that, we will we'll move to generalized global symmetries. We'll explain what those are. All right. So, first, section 1, ordinary global symmetries. Okay. So, this is going to be, I think, mostly review for most people, but I just want to sort of orient us and give us some common notation to work with. So, let's start with the simplest global symmetry that we can have, all right? So I want you to imagine your favorite quantum field theory with a U1 global symmetry. And, oh, sorry. Yeah, thank you. Okay. So for example, you can really do what I'm going to do from almost anything, but I'm going to just imagine a complex scalar field. Okay? So the action of a complex scalar field is the following. It's integral d dx, and then we have delta phi dagger, delta phi, plus v of phi dagger phi. Okay? And so let me just say right now that we're mostly going to be in Euclidean space in most of these lectures. So we're going to be in Euclidean RD, where this d will take various interesting forms as we go. Okay? Okay. So here's a complex scalar field, okay, and we're going to assume, so here's the kinetic term and here's a mass term. We're going to assume the potential has, at least a mass term and also some sort of self-interaction. So for example, we're going to take the potential to look like this. Phi dagger phi square, okay, and so on. All right, just a normal garden variety complex scalar field. And now, this thing is a classical action, okay? But we all know that we can make it into a quantum theory, right? The classical action defines a quantum theory. And to make it a quantum theory, what you do is you take the classical action and you throw it into a path integral, right? So we have something like this. You integrate, do a path integral over all complex scalar field values, and you get this. Okay? Okay. Now, what are the global symmetries of this theory? Okay. We know very well that this theory has a global symmetry. It has a U1 global symmetry. That's how I introduced it. Okay. So it has a U1 global symmetry. What does the symmetry act on? Okay, in fact, I'll write that down, even though it has an obvious answer. And it acts on the scalar field, right? So we have phi of x go to phi prime of x, which is e to the I alpha times phi of x. This is the U1 global symmetry. Okay? It's global because alpha is just a parameter. Alpha is a parameter which does not depend on space-time. That's why it's called a global symmetry. Okay? Now, the action obviously is invariant under that global symmetry. That's the whole point. Now, another basic thing, through Noether, we can construct the conserved current for this symmetry. And this conserved current is defined to be something like this, minus phi d mu phi dagger. Okay? Now, this current is conserved, right, through Noether's theorem. And the fact, whoops. Okay. So as far as I can go. And the fact that this current is conserved means that classically, rather on shell, we have that d mu j mu equals to 0. So this is true on a solution to the equations of motion. Right? It's just basic Noether's theorem. Okay. Now, this classical conservation equation is just tiny, slightly modified in the quantum theory. All right? Let me just remind you what becomes of this in the quantum theory. So in the quantum theory, meaning if you take this and you put this into a path integral, so if you now do Noether's theorem in the path integral, you find that this thing is almost always conserved. It's conserved up to what are called contact terms. Okay? So what do I mean by this? Imagine doing the path integral with some insertions of the current operator. Because we're doing the path integral, we now get sort of expectation values around things. And you can show the following thing. If you imagine computing the divergence of J in the presence of this field phi, who is charged under the symmetry, the right-hand side of this isn't quite 0 like you might have naively expected. Instead, you get a delta function at the location of the insertion. Okay? So this is actually going to be important, so I'm just going to emphasize it again. If you compute the divergence of J in the presence of the insertion of a charged field, then it's not exactly 0. You get a delta function contribution when this thing collides with this thing. Okay? People have seen this, right, in a quantum field theory class? Yeah, okay, good. This is called the Ward identity. All right? And it's not always presented as an, well, depending which book you're reading, it's a fact, and it's actually a very important one, because you should really think about this as sort of defining what it means to be a charged operator. A charged operator is something that when you take its two-point function with the divergence of the current is not 0. That's like a definition of what it means to be charged. All right? Okay. Now, Finally, one more sort of well-known thing is that global symmetries let us define a conserved charge. So global symmetry implies that we have a conserved charge. So again, let me just remind you, how do we construct a conserved charge? So normally in Lorentzian signature, we do this in the following way. We take Q of t, which is defined to be the following. You integrate over all of space. So R d minus 1 is space, because my total number of dimensions is d. And what I integrate is J0, the time component of the current. Right? So I integrate this over all of space. So here x lives in R d minus 1. Okay? Now, this thing is conserved. It's time independent. Let's just remind ourselves why that is. So people can see the bottom of this, right? This is fine, yeah? Okay. So let's compute d dt of this thing. So this is, of course, integral d minus 1x of partial t j0, where this thing is integrated on time and space. But because this is divergenceless, dt of j0 is equal to the spatial divergence of di ji, right? So what we get then is that this is equal to di ji of t and x. And now this is the integral over all of space of a spatial divergence, which means that this is a boundary term. Which means that it's 0. Okay? Assuming, of course, that in this integral I go far enough away that nothing interesting is happening, so I can neglect the boundary term. Okay? So this is, again, an extremely standard calculation that you've all seen a million times. But I want to now draw a picture of what's happening here. Okay? So let's think about what's going on. You see, in a theory that has this symmetry, like this one, what this is saying is there's a conserved particle number, right? So what that means is you have a bunch of particles. Okay, so here, in this picture, this is time, and these are spatial directions. So if you have a conserved particle number, you should imagine that here are some particles, okay? Their number is conserved, and they trace out trajectories in time. And now what are we doing here? We are doing an integral over a constant time slice. Okay? So this is the integral that we're doing. Because the particle number is conserved, we can take this integral and we can evaluate it at later times, so we can slide this thing up or down, and we'll clearly get the same answer, right? Because the particle number is conserved. That is the picture behind this thing here. Okay? Does that make sense to everybody? That's what's happening. And what I want to emphasize with this is that normal global symmetries, what this picture is just emphasizing is that normal global symmetries count particles. All right? Now, they might count other properties of the particle, like each particle might have a spin. Maybe you're counting the spin of all the particles or something like that. But it's something that's intrinsically associated with a particle number, and that comes from the fact that the integrals that we do are always of this form. Okay? Okay. Does anyone have any questions about this before I keep going? Is everyone happy with this? Okay. Okay, good. Now, let me just say another fact. It's, again, kind of obvious. So what is it that is charged again? The thing that is charged is this field phi, this local field phi. How does phi enter into this picture? You see, the field phi is the object who creates a particle, right? If you act with the operator phi, the local operator, it creates a particle at that point, and then that particle goes on and does its thing, right? That's what phi does. So let me just again write some words for that. A normal global symmetry counts particles, and here's a slightly odd sentence. The charged object creates the thing that the charge counts. Okay. So this is beginning to bring us into a terrible linguistic problem with this field, which is that, you see, the word charged and the word charge are two completely different things, okay? Let me just stress what's happening in this case. The charged object is the thing that transforms. That's phi. It's charged with a D. The charge is this object, okay? This codimension 1, this time slice integral, okay? The charged object is phi, and it creates particles, which is the thing that the charge counts. Okay. Again, I'm belaboring this because it's going to be less obvious in a bit. But if you're ever confused whether or not I've added the D at the end of my sentence or not, please just ask me. Okay? This D carries a huge amount of weight in the field of generalized global symmetries. Okay. Now, and there's finally just one more bit of formalism that I want to introduce, which is that it's often very helpful to imagine coupling in an external gauge field. Okay? So helpful to have an external field A mu. Okay? So what is the point of this field A mu? The point is that when you have a global symmetry like this, you can couple an external gauge field to it. And the way you do this is that you demand that the combined system of A and phi is invariant under the following symmetry. A goes to A plus d alpha, phi goes to phi times e to the I alpha, where alpha now can depend on x. Okay? So previously alpha was independent of space. Now you say that alpha can depend on space and time. Okay? And you can then consider the following combined action. Dagger phi, where d phi equals to partial mu minus IQ A mu phi. Okay. So because of the structure of this gauge covariant derivative, if you do this transformation on the fields, this whole thing transforms nicely with an overall factor of e to the I alpha. Okay? Now, I've put a semicolon between these two things in the action because A is an external field that we apply for our convenience. Okay? This is just a useful thing for us to do. Whereas phi is the dynamical field that exists in the path integral. So for example, when you do the path integral, what you do is you integrate over phi, do the path integral over phi, but you keep A around for the ride. Okay? So you integrate over phi, but A just goes along for the ride. Okay? I'm going to try to stick to a notation where external fields are lowercase and internal fields that we path integrate over are uppercase. I'm going to try to do this. We'll see if I succeed or not. Okay? Okay. So I want to note that this invariance has a consequence on Z. You see, this invariance survives after you do the path integral, which means that if you take the external field and you shift it, oops. If you take A and you shift it in this manner by the derivative of a scalar, then the partition function is the same. this statement is the same as the fact that we have a U1 global symmetry. Okay, so this is sort of part of the usefulness of having this external field. You can sort of diagnose your symmetry by noticing if I can do this, that means that I have a conserved current. Okay? Have people seen this kind of thing before? Some people are saying no, some people are saying yes. Okay, it's just a trick that we do to get a sort of useful knob to pull on to sort of play with the system. Okay? Okay. Now, now is a good time to ask, are there any questions about this? Is everyone happy? I'm now going to try to erase the board in the German style, so we will see how this goes. I meant to use this thing. Is that what we'll use? Yeah.
Like do it dry if you prefer.
I feel like when in Rome, you should, yeah. So let's see. So okay. Yeah.
Could you explain a little bit
Yeah.
more why this property is equivalent to having a U1 global symmetry?
Very good. Okay. So that's an excellent question. So there are a couple of ways to see this. I'll do one that's formal and one that's sort of maybe a little bit less formal. So you see what I did here? It's okay. Thank you. You see what I did here? I started with the global symmetry, right, where alpha was space and time independent, and then I promoted this to something which depends on space and time, right? And this transformation is clearly associated with that, right? I added this extra field in order to make it possible for me to write something that was invariant in this way. I could not have done this operation if the global symmetry did not already exist, okay? So I simply could not have set that up, and it is this which leads to this property after I do the path integral, okay? Okay, there's another way to say this, to be more operational. It turns out that once you have this guy, I'm now going to make an assertion which we can check in the exercises, you can extract the current in a useful way by differentiating Z with respect to A, okay? This is a way to get the current out. If you then combine these two things, you'll see that what you get is that this object is divergenceless, okay? From this statement, you can prove that d mu j mu equals to 0. And that's a more operational, less philosophical way to get the same result, okay? Okay, does that make sense? Okay, good. Excellent question. Other questions? How are we doing on time, actually? Okay, only half an hour. Good. Once I'm on track. Okay. So let's see. I think I'll do one more board and then. Yeah.
Switch to the blackboard.
Oh yeah, sure. Okay. So I'll do this one as well. Yeah, this is way better than. Yeah, this is pretty good. Okay. I'm going to have to bring one of these back with me. All right. I think this will get me through the next half hour. Okay. And then is one meant to dry it with this thing?
Turn that thing as well. And then
Turn which thing? Oh, this. Oh, I see. Just the other side of this. I see. Very good. Yeah. Okay. You've already done that here, and I guess I should be doing that here too. Is that right? Just this side, or? Okay. Okay. It's pretty dry already, though, I guess. Okay. All right. Okay. So, okay. So what I just gave you in the last 20 minutes is a sort of whirlwind tour of global symmetries. Now you should ask the question, okay, global symmetries, we talk about them a lot, but what are they good for? Why do we like global symmetries so much? Okay. And now I want to tell you about that. And this is what is really called the old Landau paradigm. Okay. So one of the things that global symmetries are really good for is that they let us classify the phases of matter. So when I have this global symmetry, there are basically two different phases that you can have. Okay? So let me explain what I mean. The first is the unbroken phase, when the symmetry is, like it sounds, unbroken. So in the complex scalar field example that I told you about, this happens when, for example, m squared is greater than 0. Okay? So the potential in this case, it looks like this. It has just a single unique minimum at phi equals to 0. Okay? This is also what you might call the normal phase. This is what you normally study in quantum field theory first. Okay? And here, the U1 symmetry is unbroken. And, there's various ways to see this. So, for example, the vev of phi is equal to 0, right? Because the minimum of this potential is at 0. So phi is going to be sitting at 0 mostly. So the symmetry is unbroken. This is invariant under the symmetry. I want to point out another fact about the unbroken phase. Let's imagine calculating phi dagger phi in the unbroken phase. Okay? So this is just a sort of normal thing in quantum field theory. Okay? It's the kind of thing you calculate in your quantum field theory class. You'll probably remember doing this. You can do some sort of, if you ignore the interactions, you can do this calculation exactly. There's like Bessel functions and so on involved. And at large distances, in other words, as x goes to infinity, this thing scales like this. It goes like e to the minus m times the distance of x, right? This is how this correlation function behaves in the unbroken phase. Have people done a calculation like this ever? People have? So sort of conceptually, what's happening here? Why does this behave like this? The point is that what we're doing is we are making a particle here. Okay, so phi dagger phi, it tells you what happens if you create a particle at x and then allow it to propagate and then annihilate it at some other distance. You create a particle at the origin, you allow it to propagate, and then you annihilate it at some distance x, which is separated, right? Now the point is this particle has mass, so it sort of costs a lot of action to propagate. This action, this cost that it has, scales like the length of the distance between phi of x to phi of 0. And that's why this thing goes like e to the minus mx, because you create the particle and propagate, destroy it somewhere far away. It has to make it there. Okay? It has to make it there because its number is conserved, right? So it actually has to make it there. It can't like decide to, it can't be lazy and say, oh, I don't exist anymore. It can't do that. It really has to exist all the way till you annihilate it. Okay? So in that sense, this behavior is intimately related to the fact that there is a symmetry. Okay? The fact that you get this for this. Does that make sense to everybody? What's happening? Okay, good. Now, this is the unbroken phase. All right? Yeah. Yeah.
So does the interpretation depends on the conservation of the number of particles, no? But the actual mathematical expression also depend on the experiments of the symmetry?
So the way to answer that is to ask, imagine that I break the symmetry, then does that still work? Right? That's really the way to test that answer operationally. So if you broke that symmetry, say by adding a term like phi cubed, say, then this would no longer be true. Okay? The reason is that if you add a term like phi cubed, there is nothing special about the point phi equals to 0. The field phi will then sort of roll off and sit at some random other point. And then this thing will then get contaminated by the fact that the vev of phi will no longer be 0. Indeed, you will not find a correlation function of a single operator by itself if the symmetry is broken. That's a really good point, and it's going to be important for the generalization we're going to come to. Okay? Good. Other questions? Yeah? There's actually a Z2 symmetry in the normal real scalar field. Yeah. Yeah. If you break the Z2 symmetry, then it's like what I just said, actually. Yeah. Yeah. It's important that I'm not talking about the connected correlator here. I'm talking about just the moment, the 2-point function. These are different things. Yeah, yeah. The connected correlator. yeah, absolutely. For the connected correlator, this is not true. Generic connected correlators actually behave exponentially, yeah. But it's crucial I'm not talking about that. Yeah. That's again another good point that I should emphasize. Okay. Yeah. Okay. Good. Other questions? Yeah. Yeah. Okay. All right. Now, of course, there's another phase, right? Which is the spontaneously broken phase. So the spontaneously broken phase is when you have m squared less than 0. In other words, V now looks like this. Okay? Right? Okay. What happens then? So classically, what happens is that the scalar field no longer wants to sit at 0. The origin of the sort of lowest energy point is going to be here now, okay? And of course, this is a complex scalar field, so there's actually a sort of a U1 rotation. I've not drawn it properly here. This is really this, the bottom of the wine bottle potential that we know about, okay? So the minimum now is not at 0. The minimum is at phi dagger phi equals to lambda over 2m squared, if I did the calculation correctly, which I'm going to call v squared. Okay? So this distance is v. Okay? The minimum is not at the origin anymore. All right? And you see, now if you act on it with the symmetry will rotate this thing by a phase. So acting on it with the symmetry will, of course, just bring me around and around the bottom of this wine bottle. All right? So that's why we say the symmetry is spontaneously broken, because it's clearly not invariant anymore. Okay. Now, I want to say a few more things here. Let me first, I want to now parameterize the interesting degree of freedom. There's an interesting degree of freedom here, which you can sort of suck out from the rest, by writing phi of x equals to v of x, where v is a field now, but basically it's this guy, this modulus, okay? Times e to the I theta of x. Okay? So here theta is a phase field which takes me around and around this bottom of this potential. Now, here's a question. What can I say about the dynamics in this broken phase? So can I say anything about the dynamics? And the answer is yes, I can say a lot about the dynamics, actually. So in particular, what you can do is you can take this ansatz and plug it into the action. I didn't do this border racing as well as you did. Anyway, don't worry. Yeah. Oh, sorry. Thank you. So if you now look at the action that you have here, so take this and plug this into this action over there, then what you find is that you can derive a low energy effective action for this field theta, which looks like this. V squared d theta squared, okay? Plus blah, 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 all right? So how do you get this? What you do is you plug this into the action and expand everything, and what you find is a field d theta squared, and this field theta is massless, right? Theta is a massless field. There is no mass for this field. And there's a good reason why it's massless. It is massless because of Goldstone's theorem. Okay? Goldstone's theorem tells us that whenever we have a spontaneously broken continuous symmetry, there will be a massless mode in the spectrum. Okay? Philosophically, that massless mode just corresponds to moving around the bottom of this potential. It clearly costs no energy to move because of the symmetry, and so you might expect that the field is massless. Okay? So I just plugged this thing into this classical action and told you this is right, but this is really very powerful. It tells you that no matter what happens, no matter how much quantum stuff goes on, there's a theorem that guarantees that the field will remain massless. Okay? So we're going to prove Goldstone's theorem again in a little bit because we're going to generalize it to a slightly more complicated setting. Okay? So that's coming again. Now, let me describe another way to describe the broken symmetry. let me consider the limit. So by the way, I should have said here that the vev of phi is non-zero. The vev of phi is given by v times some phase, which is basically arbitrary. Okay? Now, let me talk again about the two-point function of the field. Okay? I now want to ask what happens to this two-point function in the spontaneously broken phase. Okay? So let me imagine separating these two by a large distance. Okay? Now what happens? If you separate these two by a large distance, then in any local field theory, there's a principle of cluster decomposition, which says that if you separate these two things by a large distance, it should basically break into a product of two fields. Okay? That happens in any local field theory. And what that means is that at large distances, this thing should go like the product of these two fields. Okay? So this follows from what's called cluster decomposition. And now this, on the other hand, is now v squared, right? Because the vev of phi is v. Right? So note what's happened. I've taken a two-point function, and I've separated the 2 points by a very large distance. And this two-point function saturates at some non-zero value. Okay? In other words, no matter how far I take these two things apart now, the answer to the two-point function does not care about the separation. Okay? So let me write that down in words, because again, it's important. This two-point function saturates and is independent of the separation. Okay? I should say, by the way, it saturates and is not equal to 0. Okay? This one, that one also saturated, but it's saturated at 0. And in the sense, that one, you see, always cared about the distance, right? If you double the distance, that thing gets smaller. That's not true over here. At some point in the spontaneously broken phase, it does not care about the distance anymore. Whereas the unbroken one, this is the spontaneously broken answer, the unbroken one always keeps getting smaller and smaller and smaller. If you zoom in there, it keeps getting smaller and smaller and smaller. It never actually saturates. Okay? So in that way, there is a qualitative difference between the two-point function in the spontaneously broken phase and the two-point function in the unbroken phase. This way of formulating it is sometimes called off-diagonal long-range order. Okay? Or, okay, that's the acronym. Yeah. All right. Any questions about this stuff? Is everyone happy with this? Okay. Yeah, sorry, my notation is, I'm all over the place notationally. Partial theta is the same as d theta squared for me, even though it obviously shouldn't be. So when I say partial theta squared, I'm going to mean d mu theta, okay? And because I'm going to be mostly in Euclidean RD, raising and lowering is not important, but I'll be in polar coordinates for one lecture, you know. So. Okay, good. Other questions? All right. Okay. So I just want to emphasize the two-point function behaves very differently in the two phases. All right. Now, these are phases, okay? And when I say phases, I mean that they hold in macroscopic parts. If you imagine taking parameters of your theory and tuning it, so if this is m squared, then everywhere where m squared is positive, I have the unbroken phase. Everywhere where m squared is negative, I have the spontaneously broken phase. But you can also ask what happens right at the middle between the 2 points, right? That seems interesting. So let me now tell you what happens in the middle. So I'll do that here, I think. Okay. So right at the middle, so at m squared equals to 0, we have the phase transition between the two different phases. So let's understand what this means. You see, the size of the correlations is controlled by M, right? M sort of tells you, if you're looking at the system, what the correlation length in the system is. As you take M smaller and smaller and smaller, there are larger and larger and larger scale correlations in your system, okay? In particular, at the phase transition point, there are fluctuations at all scales, and you can try to understand them by just setting M squared equal to 0 in that Lagrangian, okay? So what happens there? What's happening at this point? So this point is usually described by what's called a conformal field theory. All right. This is a theory that describes fluctuations that happen at all scales. All right. So if you compute the two-point function here, then what you're going to find is that this thing behaves sort of halfway between these two behaviors. Okay? It doesn't decay exponentially in space, but it also doesn't saturate in space. Instead, it goes like a power law. All right? This power law is some universal property of the theory that's determined only by the symmetries that are involved. Okay? So this is called an operator dimension in sort of high energy CFT literature, or in statistical physics, it's called a critical exponent. It's the same idea. It's some universal number that characterizes the transition between the broken and the unbroken phase. Okay? So I'll just write that down in words. This is universal and thus interesting. Okay? Yes?
About this theory,
Yeah.
I thought that it has non-trivial beta function. How can it
Yeah. I'm being very clunky here. So what's happening is that there is a 0 of the beta function. It is not exactly this. Okay? This is just a schematic for the idea. Then what you should really do is flow along the beta function and find the non-trivial 0. In fact, because you asked the question, this theory is actually very hard to deal with, this precise one, in the physically interesting number of dimensions. If d is equal to 3, which is the sort of most interesting one, then the CFT fixed point that describes this is actually a strongly coupled fixed point. It's quite difficult to actually make sense of it. So people try very hard to make sense of it. In higher dimension, you can basically ignore this term, okay? Because this is marginally irrelevant in dimensions 4 and higher. You can basically ignore this, and then this theory is just basically a free complex scalar. Okay. Yeah. Does that answer your question? No?
Yes,
Yeah. Mm-hmm. Yeah.
I remember
Yeah.
one of QFT courses that I took,
Yeah.
that one can calculate quantum corrections when you have this strictly massless case and you get
Yeah.
some potential that
Yeah.
looks like you actually have a
Yeah. That's right.
somehow related to
Yeah.
this story.
Yeah, it is. It depends. What you have to do is you have to actually solve the quantum theory and ask what is the physics described by that. And it depends on the dimension. So for example, in 4 dimensions, if you couple this to gauge fields, it turns out there is no 0 of the beta function. Okay, the potential always has some non-trivial minimum, which breaks the scale invariance, and then you do not get a continuous phase transition. Okay, so maybe I should actually, good. This is a good point. Let me dig into this a little bit more. You get a conformal field theory if your phase transition is what's called continuous. Okay. Now, in any physical system, you might also have a sort of first order or discontinuous phase transition. Okay? That's what happens in many cases. That sometimes happens due to quantum effects. And then you can't really do anything cool. Then it's just hard and you can't calculate anything nice. And you just kind of usually hope that this doesn't happen in the system you're studying. Because if it does, then your paper is less interesting than it would have been otherwise. But in some cases, like for example, U1 in 3 dimensions, you do generically get a continuous phase transition. And that's the case that I'm sort of pointing to here. Okay? Yeah, these are excellent questions. Good. So just to say, there's a lot of work that you have to do to get to this point, which I'm completely skipping over all of it. But morally speaking, you can sort of imagine that this is what you get if you set m squared to 0 in that theory. Okay? Then you get some sort of massless field theory, which will have power law correlations. And then you want to calculate what those numbers are, and then it's very hard, and it's a big industry. But that's morally what you should imagine. Okay? Okay. So I want to point out that, you see, from this point of view, the reason why the QFT point exists is to be the phase transition between a phase where the symmetry is broken and a phase where the symmetry is unbroken. That is what the role of a QFT in life, to be a phase transition point. Okay? Okay. Now, let me now just sort of summarize everything that I've said. I went into some detail in this example, and the reason why is that in this example, the symmetry tells us how to characterize phases and the transition between them. Okay? Is there a question there? Yeah.
Yes, regarding the conformal field theory.
Yeah.
I only see that if the theory is massless, it is scaling invariant.
Yeah.
But not necessarily conformally invariant.
Yeah.
Can you distinguish these cases?
Yeah, good. Okay. So in 2 dimensions, I believe there's a theorem that if you have scale invariance and unitarity and probably Lorentz invariance, then you get conformal invariance. I keep forgetting the situation in higher dimensions. I believe in 4D there's also a proof. Does anyone remember what the situation is? In most physically interesting situations, scale invariance plus unitarity does seem to imply conformal invariance. But I say most because I can think about things where it's not true. So I think to be safe, you should really look carefully at what's going on. But there are theorems that establish this to some level. I think in 4D it's actually there is a theorem, but we should look at this again. Yeah, I think in 4D there's a theorem.
I think all of the cases where you have these conditions, all of the examples that you know are actually conformally invariant.
What about Maxwell theory and dimensions not equal to 4? I kind of think that one is actually always scale invariant and never conformally invariant. Yeah, some people are. Federico's nodding. So yeah, that's why I changed my sentence halfway through answering. Yeah. We should look at this. I think a statement is that, you see, the way I'm thinking about this, though, the symmetry is realized in a sort of normal way, linearly on the field. I think in all those cases, it's probably true that scale invariance implies conformal invariance. Although I'm saying that more as an anecdotal statement than because I have a proof in mind. But this is a good point. I think that for these lectures, it's not going to be important, but it's a good thing to keep in mind that it's not so obvious where the conformal invariance comes from, but it seems like it is often there. Okay, so it is often there. It's there in real life magnets, for example, even though there's no obvious reason for it. Yeah.
I think I missed the point. In what
Yeah.
sense is this delta universal?
Very good. You can imagine very different systems with the same symmetries. Okay, so for example, you could imagine this complex scalar field that I wrote down, okay? Or you could imagine, say, a system of clocks where you have a phase, the minute angle of all the clocks is correlated. Make it a continuous clock. It's a really good clock. And this is they're all correlated with some sort of action, okay, some lattice model. And then that lattice model will also have a phase transition point. And the delta for that thing will be exactly the same as the delta for the model of clocks. Okay? This is super non-obvious that this should be. It's happening because the symmetries and the requirement of conformal invariance alone are enough to completely fix what these numbers are. Okay? So that's a very good point. Yeah. That's sort of this moves into my next point. You see, the point is that the symmetries basically characterize the phase. Okay? Once you know the symmetries, you know a lot about what's happening in either phase, and you know a lot about the critical point that's connecting them, often enough to characterize the critical point completely. Okay? So that's important enough that I feel like I should write this down on the board. So okay, I'll stop very soon. So the Landau paradigm, so this is basically what the Landau paradigm is. So the Landau paradigm is the idea that phases of matter are classified by how they realize global symmetries. Okay? This is the idea of the Landau paradigm, and this is actually how we organize phases of matter basically in our everyday life, okay? And I'm going to get back to this. This is, I think, a good time for us to stop for a break. So I'm going to pause for 10 minutes or so, and then I will then give you some examples of how we use this already, and then I'll explain why it doesn't work for a lot of things and what we should do about those, okay? Okay, that's all. We'll start again in 10 minutes. 10 minutes? Yeah, okay. Starting again at 2:40. Okay, let's get started again. Welcome back. So before the break, I had basically been arguing to you that there are different sorts of things that can happen. You have global symmetries. They can be broken. They can be spontaneously broken or unbroken, or you can have a phase transition between them. And this is a good way to think about things, is what I was saying. And indeed, this is the idea behind the Landau paradigm. The Landau paradigm tells us that phases of matter can be classified by how they realize global symmetries. Okay? So let me now give you a few examples. Okay? So the first one that I'm going to talk about is closely related to the action that I've erased. Okay? And this is what's called the U1 superfluid. Okay? So what is a U1 superfluid? Well, the idea really is you take a bunch of atoms and you put them in a box, okay, and cool it down. Okay? So the number of atoms is conserved, which means there is a U1 global symmetry associated with the atom number. Okay? And what happens is that there are again two phases. So if U1 atom is unbroken, then this is what we call the normal phase. And if U1 atom is spontaneously broken, then we call this the superfluid phase, or maybe the Bose-Einstein condensate. The Bose-Einstein condensate is a name that you get when the scalar field condenses. It's a name given to what happens when the scalar field condenses, where in this case the scalar field is maybe not so obvious in the atom context, but you can build it as a sort of coarse-grained object. Morally speaking, the scalar field would be the operator who creates an atom. Okay? And you can use the ideas that I just gave you to fruitfully understand this transition. Okay? If you cool the system down, then the potential for the scalar field actually changes in such a way so that past some critical temperature, this scalar field will condense and your system of atoms will become a superfluid. Okay? So this fits very nicely into the Landau paradigm. And actually, the formulas that I wrote down they apply to the system almost exactly. There are a few differences because real-life superfluids don't have Lorentz invariance, which I assumed, and they have a background value for the charge density, which I set to 0. But if you include all those things, the philosophy of it is really very similar to what I had on the board previously. Okay? Okay. So this is the simplest, maybe from the point of view of formulas. It is not the most simple from the point of view of sort of intuition. A more household sort of phase transition is magnetization. Okay. So how does this work? So the simplest way to think about magnetization is to imagine that there's like a bunch of spins on a lattice, okay? And imagine that each of them points in some direction n, okay? The spins, they're pointing in direction n. And now there's a rotational invariance. Which rotates these spins, okay? So this R is some sort of rotation matrix that rotates each of them, okay? And then again, there are two phases, and here I can draw a nice picture. In one of them, which again you get at low temperatures, the spins are more or less all lined up. And in the other one, which you get at high temperatures, the spins are doing some crazy thing like this. Okay? So clearly, this is the spontaneously broken phase, and it's what we would call a ferromagnet. Okay? And this is the unbroken phase, and it's what we would call a paramagnet. Okay? And there is a transition point between them at some, again, you can sort of get from this to this by heating it up, and then things happen, there's dynamics, and some sort of phase transition. But you can understand this critical point between them, in some cases, from a sort of effective theory that you write down that transforms under these symmetries in the right way. Okay. Now, I'm writing this down in this way with a rotation matrix. The truth is, we often study much simpler models for magnetization. So there's one really simple model that you can do where you sort of imagine that each spin can point either up or down. Okay? It has only two possibilities, a binary bit of value, in which case the symmetry is really simple. It's just a Z2 symmetry that takes n and flips it by a sign. This is called the Ising model, and we will discuss this a little bit later. Okay? This is the simplest model of magnetization, and I'm sure most of you have studied this in some case or another. Okay. And now I want to give you one more example, and this is maybe the most familiar from everyday life, which is liquids and solids. Okay? So, thank you. So, it's amazing how I still can't remember this. Anyway, but liquids and solids. So, what is the symmetry involved here? So here the symmetry that's involved is, you basically have a bunch of atoms in a box, and they're sort of all moving around. And the symmetry involved here is translational invariance. Okay? So translational invariance is some sort of continuous symmetry, right, of the system. And what happens is, in a solid, this translational invariance is spontaneously broken because the atoms spontaneously form themselves into a crystal. Okay? So this is the phase where the translational symmetry is spontaneously broken. All right? So this is a solid where translational invariance is broken because you made it into a crystal. Just to explain to you, this is really broken. You can check if it's broken because if you act on it with a translation, the whole thing moves a little bit, and you can tell it's different, right? If you move each of these a little bit to the left, it's actually different. And so therefore, the continuous translational invariance has been broken down to a discrete subgroup, all right? In this square lattice case, the discrete subgroup that remains unbroken is, it looks like it's Z2 in this case. Z2 is the unbroken subgroup. Okay? This is not that important, but because if you translate it enough, it goes back to being what it was before. Okay? And now, a liquid is when that doesn't happen. Okay? So a liquid is sort of that's just the name that we give to a phase of matter where translational invariance is not spontaneously broken. Okay? In other words, here translational invariance is unbroken. All right? And again, you can study the phase transition between these two things. Sometimes it's continuous, and you can get lots of fun from studying that. Okay? So because we have spontaneously broken a translational symmetry, there is a gapless mode in the spectrum here. Does anyone know what that gapless mode is? By Goldstone's theorem, must exist. What is the gapless mode? It's the phonon, exactly. It's sound. Okay? So in a deep sense, the reason why sound exists is because of Goldstone's theorem, because we are spontaneously breaking a symmetry. Okay? Okay, good. Now, that's solid, this is liquid. Okay, now how about a gas, right? The phases of matter are solid, liquid, and gas. So how about gas? How do I characterize gas in the Landau paradigm? Anybody? The answer is I don't, right? Because it seems, if you think about it, a gas and a liquid, they have the same symmetries, right? And indeed, that is correct. A gas can be continuously deformed into a liquid. Here is the phase diagram of water. Okay, I'm going to try to get this right. All right, so this is gas, this is liquid. The solid phase is somewhere over here. Okay, and this is the critical point of water, which happens at some very large temperature, which I've forgotten. notice that you can continuously go from a gas to a liquid in the phase diagram. Gases and liquids are the same phase, okay, from the point of view of Landau, because you can continuously connect them in the phase diagram. It is just a sort of accident of our lives that we happen to live here, where there's a first order transition that connects them. Okay. All right. Okay. Any questions before I go on? Okay. So this I'll stress is a bad artist's rendition of water. In the notes, there's a link to a Wikipedia page. Okay. Now, this idea is what's called the Landau paradigm. It works insanely well. It works for most everyday things you have lying around your house, but it doesn't work for everything. So now here's a biased list of things that don't fit into the Landau paradigm. Okay. So here are some things that don't fit. Okay. So this is physics beyond Landau. Okay. So basically, everything involving gauge theory. Okay. So what do I mean by this? So you've all studied gauge theory in some form or another. There are different phases of gauge theory, right? There's the Higgs phase, there's the confined phase, and so on. You know, what are the order parameters for these things? What global symmetries do they break? This is not so obvious of a question, okay? We have tools to deal with this, and we're going to develop some of them now in the course of these lectures, but it is not so obvious what the global symmetries are that are broken in the Higgs and the confined phase. In particular, there is no local order parameter that can separate the Higgs phase from the confined phase from the sort of nice ordinary phase, the Coulomb phase of a gauge theory, okay? Yet these really feel like different phases. Okay, so what's going on? How do I classify the phases? All right. Number two, there's a whole class of things that are called topological order. Okay, by which I mean the fractional quantum Hall effect, which I mentioned is one of them, but there are many other examples. Okay. Indeed, a lot of condensed matter theory, modern condensed matter theory, sort of involves thinking about phases that sort of see the topology of the manifold that they're placed on in some interesting way. There are phases of matter, like this one, that if you place them on a sphere, okay, so take a ball and put your fractional quantum Hall effect on it, the ground state will be unique, but if you place it on a torus, then the ground state will now be degenerate, okay? So what happened? How is that possible? That does not fit into ordinary Landau. Okay. And most of what I'm going to say is going to involve these two things. You'll see this is not really unrelated to this. There's a reason why these two things are sort of the same idea. We'll discuss this in detail. And I just want to list some more things that I also think fit outside Landau to some sense or another. And these are things that I will not talk about in the lectures, but that you can learn about, and they're quite fascinating. So metals are what are called Fermi liquids, and there are so-called non-Fermi liquids, okay? These are things that happen when you take a bunch of metals, and Pauli exclusion is very important. They form a Fermi surface. All kinds of stuff happens. There are very fascinating transitions. The problem of high TC superconductivity is intimately related to the fact that we don't really understand non-Fermi liquids very well. And this is something that is, I believe, outside of the normal Landau paradigm, okay? There's something called deconfined quantum criticality. I have put a link to a review in the lecture notes. This is a cool thing. Really, what's happening is this is a sense in which quantum anomalies manifest themselves in an important way in real condensed matter systems, okay? And there are actually many examples of this, but I think this is one of the coolest, which is why I'm listing it here. It's just an advertisement to read about deconfined quantum criticality. It's really cool. It is outside the normal Landau paradigm. It involves anomalies in a fascinating manner. And finally, here's my favorite one, which I actually will not be able to tell you anything useful about. And gravity is a thing. It's a very weak statement, but gravity exists. And it's obviously very deep in many different ways. You see, there is a thing, there's a massless graviton, right? The gravitational force is long range. I don't think I really understand why at some deep level, okay? And as we go, you'll see that there are many long-range forces in nature. Like, for example, you can hear me talking, right? That's because sound is long-range. Why is sound long-range? It's long-range because it's the Goldstone mode of some sort of translational symmetry. Okay, we just discussed that over there. Now, you can see me because of light. We're going to talk about light, but there's a good reason why light is massless. And gravity is different in that I don't really have a good understanding why the gravitational force is long range. It clearly is, but there's a sense in which something is missing. I would love to know more about gravity. I have nothing intelligent to say about it, though, so that's all. But keep it in mind as I go. Okay, so these are some things that are outside Landau. Okay, in these lectures, we're going to talk about these two, all right, and try to understand this in great detail. Okay, okay. Any questions before I keep going? All right. So the goal of these lectures is to extend the framework of global symmetries to think about generalized global symmetries, which will take two forms. I'm going to discuss higher form global symmetries, which, if normal symmetries are related to particles, higher form global symmetries are related to extended objects, like strings, branes, and so on. This sounds really sort of esoteric and only for string theorists, because I said the word string and brane, but that's not true. These are really relevant for real life. You're going to see these symmetries exist in real life and in very, very ordinary systems. Okay? The other direction I'm going to extend these symmetries in is something called non-invertible global symmetries. This is a slightly newer topic, but it's also something that exists in real life. They have to do with anomalies. And basically, they involve systems where the operation of acting with a symmetry cannot be undone. We're so used to this being undoable that it seems very basic, right? You rotate your spins that way, rotate them this way. Of course you can undo it. What do you mean you can't? And you rotate it this way, then what? You know, but there's a sense in which there exist symmetries that cannot be undone. I'll explain what that sense is and how it's still very useful. Okay? Okay. Now, to do that, though, we need to generalize our idea of symmetry. And we're going to do that by first revisiting normal symmetries. In particular, this is a really important idea. We are going to understand symmetries. Actually, did I use this board yet? No. Sorry, I'm not going there yet, actually. Sorry. I'll just keep going here. Yeah. Sorry. Just making your life maximally hard. Yeah. So we are going to understand symmetries as topological operators. Okay? So the point I'm going to make for the next few minutes is that the existence of ordinary symmetries, like the one I just talked about, is intimately tied, is actually equivalent to the existence of certain topological defect operators in my theory. They're the same thing. You've actually already seen this, but I'm going to sort of make the formalism very explicit now. Okay? And the point of doing this is to obtain a more refined understanding. And the reason we need this refined understanding is that everything I just told you, though it's correct, is sort of very old-fashioned, right? I mean, you know, like I took my fundamental field phi of x, and you know, I rotated my fundamental field. Sorry, this is outside the camera. It's just a throwaway thing, though. I took my fundamental field phi of x, and I rotated it in this way, e to the I alpha phi of x. What is phi? It's a fundamental field in the Lagrangian, but you know, what does that mean? You know, we live in an age of duality where gravity can be dual to a gauge theory. The notion of fundamental fields is very fluid, okay? You can do a duality and get a different set of fundamental fields. It would be good to have a formalism for symmetries that does not care about what the fundamental degrees of freedom are, that works purely based on like sort of observables, okay? So that is the goal of this section. We're going to recast the idea of symmetries without talking about fundamental fields, okay? Okay, so let's take a step back, okay? So number one, if you have a symmetry, so if you have a U1 symmetry, then it is a fact that there exists a vector operator in your theory who is almost always conserved, okay? I'm going to now start using a form notation. In form language, where j is a one form, the one form corresponds to lowering the index on this j. This thing over here is equivalent to this d star j equals to 0. Everyone happy with differential forms? Okay, good. If you're not, on the off chance that you're not, you're just nodding for peer pressure, you can just take a look at the second chapter of Carroll. That'll teach you everything you need to know. It's mostly just notation. Okay. Okay. Now, I want you to consider the following operation. All right? Take a codimension 1 manifold. Codimension 1 means that it has dimension 1 less than my ambient space. So take a codimension 1 manifold, m sub d minus 1. So I'm going to try to indicate the dimension of the manifold with d minus 1. We're going to start changing this in various ways. If ever it's not clear, please just ask me what the dimensionality is. It's going to be important. And I want you to consider the following integral. So construct Q. Q depends on M. It depends on my choice of manifold. And it's defined in the following way. So I'm going to first write it in human notation and then in form notation. So this n, okay, so I'll draw a picture in a second, but let me, okay. So what's happening here? So I have taken my codimension 1 manifold, okay? Here it is. There's a normal vector to that manifold everywhere, okay? And what I'm doing is I am dotting j into the normal vector. In other words, I measure the flux of the current j through this surface, this codimension 1 manifold. Okay? This is a completely reasonable thing to do. In form language, this looks like this, right? J is a 1 form, star j is a d minus 1 form, and I can integrate a d minus 1 form against a d minus 1 manifold. Okay. Okay. Now, Q of m looks like it depends on m. Okay? But it doesn't, right? Q of m is actually independent under small wigglings of m because j is conserved, right? I have a flux of a conserved current that doesn't care about the surface you integrate the flux over. This is the crucial point, so I'm going to write this down. Okay? Q of m d minus 1 is invariant under small deformations of m d minus 1. It's what is called a topological defect. Okay? In other words, I can take this object and I can take my manifold and bulge it out a little bit, over there. The answer is the same. Okay? And this again happens because d mu j mu equals to 0. So there's a definition here which I'm not going to write down because it's clear, I think, from this, but just to be completely clear, a topological defect in any theory is something which is invariant under small wigglings of the thing where it's supported on. Okay? Is that clear to everybody? This word, topological defect, I'll use over and over and over again. Okay? This is the main point. So this is, by the way, the exact same integral that we did when we were sort of counting particles, except there we did the integral over a time slice. In other words, I picked my m d minus 1 to be a flat time slice. But why? I mean, you can pick it to be anything I like. The point is you can bulge this thing out. You don't need to be just at a constant time. You can do it in any sort of curvy way. You will obviously get the same answer always. Okay? Okay. Any questions about this? This is really the main point of today's lecture, to be honest. So everyone's happy with this? Then, yeah. Yeah. Why is the word defect? This is not actually silly at all. this is the standard lingo, and I just thought it was just defect because I think one of the reasons why is that the origin sort of comes maybe from condensed matter theory, where you imagine you have a metal and then you like take out one atom and there's a defect. It's just really, it's like a hole there and how that thing affects it. So that might be one reason why. It turns out in modern years, though, the word defect, topological surface, topological defect, topological operator, they actually have subtly different meanings. We can revisit this again later, but a defect is the best of all of them, okay? In that it's topological, but also it has a well-defined Hilbert space living on it. If you rotate, sorry, we missed the, yeah, excuse me. It also has a well-defined Hilbert space living on it. So this is a bit beyond what we're saying, but you can imagine rotating the defect so one leg lives in time, then you can imagine doing quantum mechanics on that time direction. A defect is the best in that the Hilbert space living on that defect is well-defined, okay? This will not be important for what we're saying. I will use the words topological surface, topological operator, topological defect more or less interchangeably. Okay, okay, good question. All right. Now, let me therefore stress that whenever you have a global symmetry, you get a codimension 1 topological defect. Okay. Okay. So this suggests the idea that symmetries are associated with topological objects in your theory. That's what we're going to push on the rest of these lectures, and you can sort of already see how this could be very useful, right? You know, why codimension 1? That's going to be the point of higher form symmetries. Okay. Okay, but first, let us rebuild the intuition that we have for normal symmetries in this new fancy language. Okay, we're going to do that first. So the first thing to do is to understand the interaction of this. Oh, I should say one more thing. You will also often see that this thing is called a charge defect as well, okay? So here note that there's no D here. It's the charge defect. I'm really sorry, but okay. But it's a charge defect because it measures the conserved charge, okay? Okay, so now I want to consider the interaction of the charge defect with a charged, see I told you, charged local operator. O of x, okay? Previously my O was my fundamental field. I now want to be more abstract, okay? And do it in a way that doesn't make use of the fundamental field nature or use the Lagrangian in any way, okay? So what is the starting point? The starting point is the Ward identity. If you recall the Ward identity that I wrote down earlier, it said that if you ever look in a correlation function of d mu j mu O, if you ever get a formula like this, that means that the operator O is charged under the global symmetry created by J. Okay? We're going to take this as the definition of what it means for an operator to be charged. Okay? From now on, this is the definition of what it means to be charged. This fits with our earlier intuition, but it should work all the time. Okay? Okay. And now you should ask the question, if I have my operator inserted here, and I have my codimension 1 topological defect, my charge defect here, imagine that I take this and sort of drag it through this operator. What happens? Something should happen, right? So I now want to carefully characterize what happens when I drag this through. Right? So I'm imagining dragging this through in this way, so I want to take this and eventually push this thing all the way through. The notion of through makes sense because it's codimension 1. You should really just imagine a piece of paper in 3D. Okay? But I can't draw it well, so I'm going to now suppress one dimension. Okay? So here's what's happening. I want to start imagining drawing this through. So now I'm going to draw this in the following way. Here's my operator. Here's my Q. Okay? So I'm going to take this. I have colors. I want to take this guy, and let me call this M1. Okay? And I want to take this thing through. That's almost the same color. I'm sorry. And move this charge thing from here to here with this local operator inserted here, okay, at O, do I call it X? Yes, at O of X. So I want to move this from here to here and ask what happens, okay? So let's do this carefully. Wow, I really write a lot. So for the people on the camera, let me just draw this picture again one more time here. So if this is M1 and this is M2, okay, and I'm suppressing the transverse direction, but it exists, okay, then the question that I'm asking is, what happens if I compute Q of M1, which is a d minus 1 manifold. So this is d minus 1, minus Q of M2, which is also a d minus 1 manifold, in the presence of this operator O. Okay? Now, these two things are topological, right? So in particular, I can take them and I can smush them together at all the points that don't hit O. Something interesting might happen there, but here and here I can just smush these two things together. In other words, this is equivalent to surrounding this thing with a ball instead, okay, which I'm just going to call this ball M prime, d minus 1. So this is therefore equivalent to Q of M prime d minus 1 in the presence of O. The prime is a lot like the 1. I'm sorry. Yeah. Okay? And now, let me call the interior of this thing BD. Okay? So in other words, BD is the interior. So delta BD is equal to MD minus 1 prime. So this thing here, the inside, is BD. Okay? That's a d-dimensional subregion whose boundary is this ball. All right? So now there's something quite useful I can do. First of all, I take my definition of Q. Remember, Q. Where is my Q? There's my Q. Q is the integral of star j over this, the outside of this ball. Okay. So this is the integral over M prime d minus 1 star j O of x. Okay. And now, let me take this here. The integral of star j on a boundary is equal to the integral of d star j over the inside by Stokes' theorem. So this is integral over bd of, whoops, I left out the d, of d star j, okay, over the inside and now I use this thing, which basically tells me that I get a delta function contribution from exactly one point over that integral, the point over the inside where I hit that guy over there. So this then is just I-O of x. Okay. So let's remember where I started with. I started by saying I have Q of M1 minus Q of M2 in the presence of O of x. What this is saying is if I drag Q of M1 through Q of M2 and I hit O, I get O on the left-hand side. Okay? So this tells you that it is not topological in the presence of the operator O. There's a nicer way to write this. Okay? And the nicer way to write this is the following thing. What you should do is, and this is exactly the same thing, if you imagine taking your operator, O, and formulating your Q on a sphere that wraps this O, okay, then what you can imagine doing is take this sphere, O of x, and just imagine taking it and collapsing it down. Okay, take this whole thing and collapse it down onto the sphere. If you collapse it down, what you get is just the same operator back again, times an eigenvalue, which in this case is I. Okay? This is the same thing as what I just did above. Okay? So because we're going to use this quite often, I will, still have 10 minutes left, yeah. I will just draw a picture of that to emphasize it. So I think I'll need maybe, I think I'll need like 2 boards, yeah. Oh, yeah, sorry. Sorry, I should have been a bit careful here. So there's a, let me call y the thing that I'm integrating over here. So I'm not taking the d of O. This is a separate, let me call this variable y. So y is the integral here. And so I'm not taking d of that, yeah. There's two, always held fixed. I'm not differentiating or integrating over anything else. I'm integrating and differentiating the other guy, the current guy. Does that answer the question? No. Yeah, that's right. Always not moving. It's really a fixed object from the point of view of all of this. Yeah, good question. Okay. So, so where were we? I just drawn this picture and told you that what's happening is you're taking this guy and collapsing it onto this operator O, and as you collapse it, you get an overall phase for this thing. Okay. Now, it is actually very convenient to define, this is the thing that generates an infinitesimal charge rotation. Remember, the charge always generates an infinitesimal charge rotation. It's very convenient to define the object that creates a finite charge rotation. Okay? So this I-O should be viewed as the small change in O. Okay? Delta O is I-O. That's how a phase rotation works. But it looks nicer to think about the finite rotation. And we're also going to see quite a few cases where we need to think about the finite rotation. So let me now construct the topological object for a finite charge rotation. And I'm going to call that u sub alpha, where alpha is the angle that I rotate through. Okay. And this is defined as e to the I alpha times the q of previously. Okay. This is always the case. You exponentiate the infinitesimal to get the finite. Okay, and it's true here as well. So let me just draw a picture of what happens when you have u of alpha. So if you have your O here, so if you imagine acting with u of alpha on your local operator O, then if you collapse it, what you get is the same operator back again, O of x, times a phase e to the I alpha. Okay? So you take this guy, collapse it onto this thing, and you get the same operator multiplied by a phase. Okay? Does that make sense? Should I write down a formula? You get the idea. Okay, I'll write down a formula as well, just to be absolutely clear. What happens is u alpha on an SD minus 1 that wraps O equals to e to the I alpha times O. Okay? And this is the pictorial version of that formula. Okay? Okay. Now, I have about 5 minutes. So I think in the 5 minutes, yeah, I think that's enough time to do what I have left for this thing. So what are some other things I can do with these guys? Okay. So one thing you might imagine is, so I've just shown you what happens. You take a local operator and drag it through, and it picks up a phase. Okay. You can also imagine taking two of the charge defects and fusing them together. Okay. What happens then? So the answer to this is quite obvious, I think. You can all guess what's going to happen. So if you want to study the fusion of charge defects, what you do is, so imagine here's one of them, here's another one of them, okay? So say this is u alpha of md minus 1, and here's u beta of md minus 1. If you imagine fusing these two together, then what you get, of course, is one guy left over, which corresponds to rotating by alpha and then rotating by beta. Okay? In other words, from the point of view of fusion, equals to u to the alpha plus beta md minus 1. Okay? And that is clearly consistent with that transformation law, and is just generally what happens. Okay? So maybe there's something important to stress here, though. What's really happening here, each of these guys is really an element. It's defining an element of the rotation group, right? In one dimension, u1, or 2 dimensions, u1. And so the way to think about this alpha plus beta is really, this is the group composition of e to the I alpha composed with e to the I beta. That's why we get alpha plus beta, because, well, in u1, e to the I alpha, e to the I beta is e to the I alpha plus beta. But, of course, it's not quite so simple if we have a non-abelian symmetry, right? Which is the next thing that I'm going to talk about. So here I will be a little bit quick, and we can discuss it in more detail in the tutorial. So how about for non-abelian? This works the same way. Okay, there's really nothing fancy that happens. You can kind of all guess how this is going to go. So just to put some formulas down, imagine we have a non-abelian group G. Okay. Then our operators O transform in some representation R of G, right? In particular, I should give this O an index A, where this tells us this index A transforms in some linear representation. All right. Now, what is a representation? A representation is, of course, a set of matrices So if I have some group element little g in capital G, okay, then a representation is defined by a set of matrices V that satisfy the following group composition property. Okay? This is what defines a representation. And now everything sort of goes through in this sort of obvious way. All right? In particular, we now have a U, a charge defect operator, which is labeled by an element of the group. All right, which we can wrap around an operator. I want B here. And when you wrap it around the operator, what you get is an action by the representation on the operator. Oops. Okay. So this is the non-abelian version of that thing. Okay? Does everyone understand how? In that case, the U1 group acted on the operator by multiplying it by a phase. Here, my fancy non-abelian group acts on the operator multiplying it by a matrix. All right? And that's what's shown here. All right? This, I stress, is a finite dimensional matrix. So for example, if we were doing SU2, this would be like the exponential of the Pauli matrices, okay? Some 2 by 2 thing maybe. This is some quantum operator. And what this is showing is how the quantum operator acts on this thing as a finite dimensional rotation in the internal space. All right? Okay. And finally, there is one more formula I want to write before I stop. And that formula is just the following thing. It involves the composition of these two things. Okay? So what happens now if you compose two of these guys in the non-abelian case? I mean, everyone can guess what happens, right? You have UG of M, UG prime of M equals to U sub GG prime of M. Okay? For every group element, I have a charge defect. If I fuse them together, then I get a new charge defect given by the group composition law. Okay. Okay. There's something very different about this formula versus that formula. The fusion rule that I had, this formula versus this formula. What is the difference? Anyone? Yes, exactly. You see, this side cares about whether G is on the left or G prime is on the left. It's different. It's a different group element. Okay, does this side care? Well, it does, right? Because they're codimension 1, there's always a sense in which two codimension 1 things, there is an ordering of them. If this is codimension 1, this is codimension 1, this is always before this. That makes sense. That's a well-defined notion. Okay? In fact, when you put these things in a path integral, which is what we're always doing secretly, they're always in a path integral, then the ordering on the quantum Hilbert space is given by time ordering, which is really saying, which one is earlier, okay? That's really what's happening here. So therefore, this is good. This formula makes complete sense. The ordering over here is inherited from the ordering in space. This is fine, okay? But again, when we generalize, that is one thing that will change. You can see that this extra structure of ordering in space only really makes sense if it's codimension 1. If it was a lower codimension, it might not make sense anymore, and then we have to think about what's happening. Okay, that is all, and I'm meeting you again in half an hour. So everyone enjoy your half an hour break, and I'll see you again shortly. Yeah.
Maybe we have some very short questions.
It's not actually a question, but a short announcement, and then I'll leave it for the other questions. Just because I didn't get where I wanted to get, I only have one exercise at the moment that that could follow the theory lecture of this morning. So what I decided to do is to still teach for like half an hour in the exercise session that starts at 5 for my slot. I just wanted to let everyone know so that you don't miss a part of the theory if you were planning something else. Right, that's all. Thank you.
Yeah, I had a question about the identity with the charge there on the rightmost part, with the sphere, the evaluation of the charge operator.
Okay.
So, I mean, usually the story, Usually the story would be that what would otherwise here correspond to the gauge field, which for you is an external field, is not globally defined on the sphere, because you need two charges to cover the sphere, and then you would have to identify the local value of the field at the equator or something along these lines, and there's an integer number of ways. And so from this, I would expect the evaluation of the charge operator to give you an integer n there, in that identity on the...
Right, yeah.
Is that, should there be an n there?
So
Should there
I
not be an n there?
I have assumed my field O has charge 1. That is correct. If this had charge Q, there would be a Q here. That's correct.
So generally there would be an integer there, which would then appear there in the transformation, the U1 transformation.
That's right. So if the general case has an integer Q, which to be honest, for some reason I bring back for the higher form case, so you'll see the Q everywhere, but it would appear everywhere, yeah. So over there it would be e to the I alpha Q.
I was wondering whether it was the fact that it's a non-dynamical field that was somehow, you know, this redundancy would somehow be lifted, but
it's not. Yeah, it's not really. To be honest, I think actually for most of what I'm saying, the integer quantization is not important. To be honest, I think it's not. I believe it has not been important yet, actually. So the global structure is really not important for this stuff, but at some point it will be important. Yeah, so anticipating slightly. Good question. Yes. Yeah, that's right. It should be here. So there really should be a number here, which is the charge of the operator O, which I've set to 1 in this case. Yeah, that's right. Absolutely. Good. Other questions? Okay. People should go get coffee, and then I'm back in half an hour, and then there'll be more questions, and we'll do some exercises. Okay. Yeah. I should say, by the way, the lecture notes have exercises in boxes. So that's what we're going to do mostly. Okay.